Hi everyone. In this video I'll be covering how to identify the electrophilic site in an alkyl halide in substitution reactions, how SN2 and SN1 mechanisms work, and how to predict which one will occur based on the starting materials and conditions. What is an alkyl halide? An alkyl halide is an organic compound where one or more hydrogens are replaced by a halogen such as fluorine, chlorine, bromine, and iodine. They can be primary, secondary, or tertiary, which refers to how many carbon bonds the carbon bound to the halide has. So here you can see that this bromine is attached to a carbon that is only attached to one other carbon, so that's a primary. Here the bromine's attached to a carbon that's attached to two other carbons, which makes it secondary. And here the bromine is attached to a carbon that is attached to three other carbons, which makes it a tertiary. Alkyl halides create an electrophilic site at their bonded carbon because of their electronegativity. With the exception of iodine, halogens are more electronegative than carbon and therefore create intermolecular dipole-dipole interactions that pull the electron density toward the halogen and away from the carbon, which leaves the carbon partially positive. This makes the carbon electrophilic, meaning that it likes electrons and is therefore susceptible to a nucleophilic attack. So as we know at this point that we denote a partial negative charge and a partial positive charge with this delta plus and delta minus. So to start with a quick review of SN2 reactions. SN2 reactions occur in a single concerted step. As the nucleophile attacks the electrophilic carbon, the leaving group departs at the same time nearly instantaneously. There's a single transition state where the carbon is transiently bonded partially to both the nucleophile and the leaving group, as we saw in Dr. Marshall's lecture with this graphic here. So as you can see here in this middle, this carbon is partially bound to both the leaving group chlorine and the nucleophile alcohol group. And instantaneously this happens, so just pretty much as soon as this chlorine is leaving, the alcohol group is binding and you get your new product here. Notably, we see what we call a backside attack from the nucleophile in SN2 reactions, which means that the nucleophile approaches the carbon opposite of the leaving group. This happens because the halogen basically does not allow access to the carbon, so the nucleophile almost has to sneak around the back to get to the carbon. So from here you wouldn't see this same configuration with the alcohol swapped completely with the chlorine. You see it more in this configuration where it kind of flips inside out almost like an umbrella. That was how it was explained to me in my previous organic chemistry class. So this will result in an opposite stereochemistry. So this is not an example of a chiral carbon or a chiral compound, but if it were, you know, say you had an R configuration here, your product would be an S configuration here. We also want to note that the rate of the reaction for SN2 reactions is second order. It is dependent on both the concentration of the nucleophile and the alkyl halide, since the reaction occurs at the same time. If it was dependent on one or the other, making it a first order reaction, it wouldn't be able to happen at the same time. So for SN1 reactions, there are two-step reactions. These are two-step reactions where we create a carbocation through solvolysis, which is where the solvent assists in removing the leaving group. So after the leaving group has departed and thus created the carbocation intermediate, the nucleophile will attack the carbocation to form the final product. So here we can see in, again, Dr. Marshall's graphic, first we have the solvolysis, which causes this chlorine to leave, and then this creates this carbocation center, which we are quite familiar with at this point. And then here is where we have the alcohol group attacking the carbocation center, and then you form, so this is your first intermediate and this is your second intermediate with this water bound, I think I said alcohol, your water bound to your original reactant. And then from here you will have a secondary reaction that will remove this hydrogen from the water that is bound, because the water is not in a happy state right now. It's positive. It's bound to too many things. So once this hydrogen leaves, and then you form your protonated water and your chloride ion, that's when you get your final product here. In my previous OChem class, I recall this being explained as how you can't easily catch a dodgeball if you're already holding a dodgeball. So you have to get rid of the one you're holding before you can worry about catching the one being thrown at you, unless you have like crazy athletic skills or massive hands or something. But that was how it was explained to me, and that was 10 years ago, so it's still stuck to this point. Here, the carbocation intermediate is planar sp2 hybridized, as we can see here. So you have both of these orbitals here that are available for nucleophilic attack. So it can attack from both sides, which will result in a racemic mixture for chiral compounds, which, if you recall, is an ideally 50-50 concentration of both enantiomers. So you would, in an ideal situation, have 50% R enantiomers and 50% S enantiomers for a chiral compound. We note that the rate law for SN1 reactions is first order here. Kind of like I said in the last one, it's dependent only on the alkyl halide concentration, because the rate determining step is this first step. So if this step isn't happening, then this step isn't happening, obviously. So the nucleophile here, it doesn't matter how much concentration you have of the nucleophile if this doesn't happen. So that's why it's only dependent on the alkyl halide. So when we want to predict which substitution mechanism a reaction will follow, we need to consider both the structure of the alkyl halide and the reaction conditions. So SN2 reactions, again, are the one-step mechanisms where the nucleophile attacks the electrophilic carbon from the opposite side of the leaving group at the same time that the leaving group departs. So bond breaking and bond forming happen simultaneously in those SN2 reactions. Reactions that favor this mechanism are going to require good nucleophiles, which we can recall that a good nucleophile is a good base, and that is primarily seen in here with these charged atoms. SN2 is also favored in the presence of polar aprotic solvents such as acetone or DMSO, and this is because they do not participate in hydrogen bonding due to the lack of hydrogens bound to oxygens or nitrogens. Lastly, we have to pay attention to the steric hindrance of the carbon. More hindered carbons, like those seen in tertiary halides, are not able to react SN2 because there's essentially too much going on around the carbon to allow room for this to all be happening at once. For it to all happen at once, you can kind of think there's a lot going on, it needs space, so if it's too encumbered with other substituted groups on the carbon, then there's not enough room for all of this to happen at once. So because of this, methyl halides are the most reactive, followed by primary halides, and then least reactive are the secondary alkyl halides. In contrast, SN1 reactions occur in that two-step mechanism where the leaving group first departs via that solvolysis to form the carbocation, which is then attacked by the nucleophile as the second step. So the SN1 reactions are favored in reactions with poor or neutral nucleophiles. They are also the favored mechanism in the presence of polar protic solvents such as water, all alcohols, and carboxylic acids, and most amines. This is in contrast due to the availability of hydrogen bonding that forms from the hydrogens bound to the oxygens and nitrogens in those solvents. Additionally, we'll see SN1 reactions where the reactant is a tertiary or secondary alkyl halide, and this is due to the stability of the carbocation, which is a very important topic in terms of if it will react SN1 or not. The more a carbocation is substituted, it becomes more stable as an intermediate. So primary alkyl halides and methyl halides are so unstable as carbocations that they won't even react SN1. So a tertiary alkyl halide is going to be a more stable carbocation than a secondary alkyl halide, and again, primary and methyl halides won't even react. So just in summary, I wanted to kind of create a page just if people wanted it all in one place. But to summarize, the electrophilic site of an alkyl halide is the carbon bonded to the halogen. SN2 reactions are those one-step reactions. They occur in the presence of good or charged nucleophiles. Polar aprotic solvents such as acetone or DMSO are also going to favor SN2 reactions. And in the product formation of SN2 reactions, we need to pay attention to that inversion of stereochemistry. So switching from R to S or S to R, like that inverted umbrella, kind of flipping inside out. Also need to pay attention to the carbon and how hindered or unhindered it is. And again, your methyl halides are going to be most favoring of the SN2 versus a tertiary won't even occur in an SN2 reaction, but methyl halide, then primary, then secondary. And then SN1 is that two-step reaction that forms that carbocation that's susceptible to nucleophilic attack. We see those in reactions with poor or neutral nucleophiles, neutral as in uncharged nucleophiles, reactions that occur in the presence of polar protic solvents, such as water, alcohols, carboxylic acids, and most amines. And then those we need to pay attention as far as our products go. They will result in a racemic mixture if the starting compound is chiral. So you'll have 50% R, 50% S. And then also important for SN1 reactions, they need to have a stable carbocation. So methyl and primary carbocations will not occur SN1 or will not react SN1, and you'll only see SN1 reactions for tertiary or secondary alkyl halides. So anyway, thank you. And if you have any questions, just let me know, and I look forward to watching all of your guys' videos as well. Thank you. Bye.